Hello everyone, my name is Sarang Patel. My topic is probability interference in bias network. Then next, objective and definition. Objective: to understand how probabilistic interference helps in resolving under uncertainty using bias network. Definition: a bias network is a graphical model that represents set of variables and their conditional dependencies using directly cycle graphs. DAG notes random variables, ages, probabilistic dependencies. Goal: estimate known probabilistic given known evidence. Essential elements of bias network. Notes: present random variables. Ages: present causal relationships. Conditional probability table quantifies how the node depends on its parents. Joint probability distribution. Bayes compounds represent the joint distribution of all variables. Example: weather, traffic, rate of work. Principle of probabilistic interference in bias network. Bayes theorem. P of H of E is equal to P divided by A P of H upon P of E. Update belief pH of after observing evidence E. Inference principle. Computer the probability of event based on the known evidence using conditional dependencies. Purpose: derive conclusion or make precedent is uncertain situations. Then types of probabilistic interference in bias network. First one, exact interference, in which variable elements interactive variables to compute a marginal probability efficiently. Belief propagation passes message between nodes to calculate probabilistic in tree structure network. Justic: the tree algorithm converts a complex graph into a tree of cons to apply belief preparation. Insummation method: computer probability by summing over all possible variables. Assignments: dynamic programming approaches, resolving intermediate result to reduce reduct computation. Next one, approximate interference. Monte Carlo sampling uses the random sampling to estimate probabilistic variable interference. Zugmit approximate complex distribution with similar ones. Looping belief propagation applies message passing in graph with cycle. Approximate version of belief propagation. Marcon's chain Monte Carlo generates samples from probability interference disturbance by constituting a Marcos chain. Particle filtering sequence sampling method used in dynamic bias network. Field and applications of probabilistic interference. Bias network enables principled resolving under the uncertainty across the deserved domains, transforming how we approach complex decision making problems in real world scenarios. First, in medical diagnosis, disease prediction and diagnosis using patient symptoms, test results, and medical history of compute fostering probabilistic condition. Next is autonomous system. Sensor fusion and decision making is the robot and the self-driving cars enabling safe navigation through uncertain environments. Financial modeling, risk assignment, and profit optimization by modeling dependency between market variables and economic indicators. Natural language processing, speech recognition, machine translation, and information extraction, leveling probabilistic dependency in intelligent structure. Pillars of probabilistic interference in Bayes network. First is graphics, second is probabilistic framework, and third is inference mechanism. First one is graphical structure. Directed acyclic graph encodes conditional impedance relationship, enabling efficiency factorization of joint probability distribution. Probabilistic framework, a mathematical foundation built on the probability theory supporting both exact and approximate interference through a resolving computational method, inference mechanical algorithm for computing marginal and conditional probability of the variable elements to message passing schemes like belief progression. Bayes network represent a computation of the modern probability reasoning, computing graph theory, and probability theory to model computer dependency. These three pillars work simultaneously to enable trackable inference in high-dimensional space while maintaining integrity. Interference technique in Bayes network. There are various methods. First one is variable elimination, justification tree algorithm, belief progression, sampling based on method, variational methods. Variational methods elements variables for efficiently probabilistic computation. Junction tree algorithm converts network into tree for local probability updates. Belief progression, passing probability message in tree structured networks generate random sample to eliminate probabilistic. Variational methods, approximate distribution for faster interference. Enhancing Bayes networks for practical application. First one is structured learning, parameter estimation, approximate interpolation, dynamic interpolation, automated discovery of the network topologies from data using constraint based on the store based or hybrid algorithm to identify conditional dependency relationship. Parameter estimation, learning conditional probability distribution for the observation using maximum likelihood elimination Bayes net approach or the expectation maximized for the incomplete data. Approximate interference method, scaling to large network through sampling techniques like MMC, important sampling and various approaches when exact interference becomes interactable. Dynamic interaction, temporal resolving with dynamic Bayes network for the modeling time series data tracking for the forecasting in the innovation system. Core applications of probabilistic interference, dynamically resolving computer POP to identify likely expectation for the observed evidence, causal for troubleshooting, and the root causing analysis, predictable modeling, forecasting future state by computing given current observation and learn template dependency, causal interference, eliminate interval effect through the calculus causal resolving to support evidence based on decision making. Next is future of probabilistic interference. The field is rapidly evolving with the emerging technique and the methodology that propose overcome current limitations and unlock new capacity. First one, deep learning integration. Second, quantum computing, and third one is scalable achievements. Next is challenges and probabilistic interference in Bayes network computational complexity. Parameters that specify models, space selection trade-offs, ethics and consideration and key issues. First in bias in prior distribution, second privacy data and protections, interpretable versus accuracy. These are some questions. Conclusion. Probabilistic interference in bias network is powerful framework for resolving under uncertainty by leveling factorization and consideration inference. Bias network reduces the complexity in the representing joint distribution. Exact interference method provide precise network but the computational interference while the approach method after scrambling with the acceptable accuracy.